Hi, it's Kevin Lebates here, and today I thought I would create a short video about number bases because they're very important in computing, and we're going to use node in order to call up a prompt. So we're now in a JavaScript interpreter, and we can type whatever JavaScript commands we like at the prompt. And what I'm actually going to do is I'm just going to type in numbers and talk about them as I do it. So let's start off with a standard number like 42. This is actually in denary or decimal. And the reason why we as human beings use decimal is probably to do with the fact that we have 10 fingers. So we have 9 digits, 0, 1, 2, 3, right up to 9. And if you want to represent a number that is bigger than 9, you need to add a second digit in order to convey that meaning. So here at 42, what we're really saying is that we have 2 units and 4 lots of 10. And when I hit the return button, you'll see 42 does indeed evaluate to 42. But it's entirely arbitrary that we have 10 fingers. We could have equally been born with just 2, in which case we would probably be using binary as human beings. And in JavaScript, you can say that you're using binary by starting your number with 0b. That means we're now using base 2, and we're counting as though we only have 2 fingers. And instead of having ones and tens and hundreds represented by the digits in the first, second, and third position, we're going to go up in powers of 2 rather than powers of 10. So, for example, if we take the number 13 in our usual denary base, then in base 2, we're going to have to work out that that is 8 plus 4 plus 1, because 8 plus 4 plus 1 is 13. And if we look at the positions of the numbers, it'll work out as 1101. And here we have one lot of 1, no lots of 2, one lot of 4, and one lot of 8. And so we end up with that sum, which I'm doing in denary because that's the number system that people think in, generally speaking. We end up with 8 plus 4, we're not adding on 2, plus 1, and we get 13. So that's kind of neat. And binary is useful in computers because computers store information as ones and zeros. And as a result, they work in binary. And the interesting thing about computers is that each memory slot for a number has a certain number of these what are called bits. When I first started working computers, we had 8-bit computers. And that means that any particular memory location in the computer could store a total of 8 of these bits. And if I just do that now, 1, 2, 3, 4, 5, 6, 7, 8, you'll see that any memory location could store numbers between 0 and 255. If you had a 16-bit machine, like for example a Sega Mega Drive console, 2, 3, 4, 5, 6, 7, 8, then a memory location could store 65,536 different numbers from 0 to that number. So that's binary. Another format that we could use is something called octal. That is the number system for aliens out there with 8 fingers. And if we start the line with 0, that indicates to JavaScript that we're in octal. And now we have at our disposal the digits 0 up to 7. So 007 is very much like our existing number 7 in the denary system. If I type 8, we're going to get an error because there is no token 8 in the octal system. So if I want the next number up from 7, I have to put octal 10. And octal 10 equals 8. And then I can keep counting up. Octal 11 is 9, octal 12 is 10, and so right to octal 17, which corresponds to 15 in our number system. And the next number up would be 20. Octal 20 is the equivalent of 16. So octal actually represents, let's see, that would be 2 bits, because in binary. So in binary, if we look at, no, it's not 2 bits, is it? It's 3 bits. I got that wrong. 100. There we go. 1, 1. Yep, 3 bits. Octal numbers would represent 3 bits. The number system that we tend to use the most when you're actually dealing at this kind of low level is the hexadecimal system. And you indicate that you're using a hexadecimal number by writing 0x followed by your hexadecimal number. And hexadecimal means that we have a base of 16. So that's like aliens with 16 fingers doing counting. And as a result, we have at our disposal the usual digits, 0 to 9, but we also get an A, B, C, D, E, F. So if you had 16 fingers, you would be kind of going 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. And then the final one would bump you up to 10, which in decimal would be 16. And the neat thing about hexadecimal is that it represents 4 bits in a binary number. So the hexadecimal number F is 15, and if we do that in binary, 15 is 1111. So one hexadecimal character represents 4 bits in a binary number. And as a result, if you're looking at a total of 8 bits, so remember that gives us the numbers up to 255 in denary. In hexadecimal, you can do that with 2 characters. There we go. And hexadecimal is what is used in Ethereum to display Ethereum addresses. So if I hop off screen and grab my Ethereum address, but I haven't got it open. That's a bit awkward. Well, I'll just grab a wrong one. I'll go and look up Vitalik Buterin's Ethereum address. Hang with me for a moment. Here we go. I found his address off screen, and I'm going to copy it now. And this is Vitalik Buterin's Ethereum address. And you can see it contains noughts and ones. Does it contain any twos? Yes, there's a 2 near the end there. 3, 4, and we've got A's and B's and E's. We don't have an F, but there could be one in there. But you're not going to see anything other than 0 to 9 or A, B, C, D, E, and F in an Ethereum address, because it is basically a large hexadecimal number. And you can see below there that it's something in the order of about a 10 followed by 47 zeros. So that's a pretty big number. That's 1 quindecillion. Normally when we're talking about huge numbers, we're talking about billions or trillions. Well, a quindecillion makes a trillion look like a teeny tiny number. You may be wondering why some of the letters in Vitalik's address are in capitals and some are lowercase. And I'll give you a hint as to what that is about. The capitalization or lack of it is used as a checksum. And I'm not going to describe the algorithm that's used in the checksum in order to verify that a particular address is valid. But if you capitalize an Ethereum address incorrectly, there are certain programs that will reject it on the basis that the checksum is not correct. So the capitals are not essential because ultimately it's just a number, but there's an extra feature hidden in there for Ethereum addresses in having the capitalization correctly so that you know that the number has been typed in correctly. I think that's kind of clever because it doesn't change the actual number itself, but it does allow you to convey a little bit of extra information. Now, of course, you can only capitalize or lowercase letters, which are still digits in hexadecimal, but you can't capitalize zeros or ones. I wonder why we don't have a capital one or a lowercase one. Well, I guess that's a question that could be dug into at some other time. So anyway, there you go, a lightning tour on base systems or number bases in computing and why they're important. And you really do need to get familiar with, in particular, hexadecimal as a programmer. I mean, you just have to know off the top of your head that, for example, 0xFF is going to be 255. That's it for today. I hope you found it interesting. Sorry about the few hiccups along the way, but I didn't really script this, so it's not going to be perfect. Hope you enjoyed it, and see you in the next video soon. Bye for now.